Hello, I'm Mr. McBrien. This is TJ20, Introduction to Hardware. Ontario would like for us to be able to use precise terminology to identify the various types and features of computer hardware and interfaces. We'll begin our investigation of that today. A major part of our computer engineering course, no great surprise, is centered around the computer. So we look at the design of it, its configuration, its repair, and how to program it. Now, in order to really understand this, we need to look at how computers are put together. We're going to focus on PCs and generally on the Windows interface to this. However, the underlying structure really is pretty consistent whether you're looking at a Mac or any other kind of computer. The basics are the same. So if we consider for a second what we see when we look at a computer, sitting under a desk, on a desk, or what have you, we see the computer cabinet. And it is very much a component of the computer, even though what it does is store all the components inside itself. If we're going to choose a cabinet, we should make sure that the motherboard's going to fit into it, and so the main types are AT and ATX. One quick safety note before we move on from the cabinet, though. The outside of a computer is made to be pleasing to the touch. The anticipation of the manufacturer is that it will, in fact, be in contact with the user. As soon as you open up a computer, those assumptions are no longer the case, and so we have to be aware that any metal edges inside the computer are sharp. Don't run your hands along them, be careful. The power supply is a critical component, even though we've named it the wrong thing in some ways. So the PSU doesn't supply power. Rather, it takes power from the wall. It takes 120 volt AC from the wall outlet and converts it typically to 12 volts DC and 5 volts for the components inside the computer. Now, the PSU is important. We need to make sure it can provide enough total power for all the components that are inside the computer. Having said that, usually a 500 watt will work. If you have a really good video card, then you might need as much as a 700 watt power supply. In general, you can pretty much use a generic PSU, but if you're being price conscious or if you're building some kind of serious beast, you can actually sum up the individual requirements for each component in your computer and specify your PSU with great accuracy. If we want to think of the PSU as the heart of the computer, then the motherboard would be both the skeleton and the circulatory system. So it's the main circuit board inside the computer, and every internal component is attached directly to the motherboard, including the CPU and the RAM. And the motherboard includes the BIOS that we'll talk about in a subsequent discussion, located on, in the old days, the EEPROM chip. Nowadays it's typically flash memory. And that BIOS will initialize and test our hardware, and again, we're going to investigate that more deeply at a later point. So the BIOS actually has all the settings for the components in our motherboard as well, and our motherboard will contain these expansion slots that you can see here that allow us to customize a computer. So we now got a skeleton, we've got a circulatory system, we've got a heart. The CPU, we can think of it as the key brain of our computer. More than 1 billion transistors are densely packed on this integrated circuit, and most of the computer processing operations occur inside this CPU. It can do billions of operations per second, and of course, this is a key thing that defines our age now, is this number of operations that a single CPU can do. Now, all these operations come with a cost. Our PSU provides us with power. However, wasted power gets converted into heat. And that heat, the CPU, generates a great deal of heat as it's doing calculations. And so it is critical to move this heat away from the CPU. We do this with a heatsink and a fan. So we can also carry our metaphor, our organism metaphor, a little further and talk about our system clock. Our system clock, we can think of it as the heartbeat of our computer. So there's a quartz crystal on every motherboard, and this quartz crystal vibrates when electricity is applied to it, causing a pulse. And this pulse will coordinate all of the operations that happen inside the computer so that the computer can know what it's doing at any given time. So for every tick, every pulse of the clock, the CPU can do one function or step. If we have a 3 gigahertz clock, that means there are 3 billion ticks per second. Now, information needs to move around our motherboard. This is the function of the bus. So, most buses will broadcast a given signal such that it moves throughout the motherboard and every component will see it. We have a schematic here that talks about how the buses interconnect our given components. So we have the CPU, our RAM memory, and various input-output devices. We have 3 different kinds of buses, each connecting every component, and we should unpack each one of these buses individually. So the data bus, go figure, moves data. And instructions can be lumped inside this data box. The width of the bus determines the speed at which data moves. So the number of wires that make up the bus determines how much data can move in a given clock tick. So we'll typically talk about bits, because 1 bit can move for each channel that we have. So if we have 32 bits, this means we can move 32 bits per cycle. And so some buses may be 8-bit, 16, 32, 64, depending on the situation. The address bus doesn't exactly carry data. Rather, it identifies the source or destination of data. So it's sending a destination, an address. For example, a CPU might need to get information, data, from a given location in memory, in RAM. And so the CPU sends that data location to the RAM, and the RAM knows to unleash, to release that data back to the CPU from that location. So the bus width here is a different thing. It doesn't determine how much data can be carried. The width of the address bus determines how many spaces can be addressed. For example, an old 8080 configuration had a 16-bit address bus, meaning you could have 64 kilobytes of space that could be uniquely addressed. So this width defines how much memory is available. The control bus, we've already talked about the system clock. The control bus transmits control and timing information. So memory read-write signals, interrupt requests, and clock signals all move through the control bus. So now our schematic should give us a little more insight into how the computer works. We have control lines, address lines, and data lines, and we know what each one should carry. So let's look at, for simplicity's sake, the retrieval of information from one location in RAM. So a CPU determines that it needs the information from a given spot in the RAM. So it sends the location for the data that it needs. And it sends these through the address lines on a given system clock pulse. And the memory recognizes that that address, the information contained in that address, is required, and it then sends that information back to the CPU. So the contents of that location in RAM is sent back to the CPU through the data lines. So hopefully this should make it a little more clear how this system works. Now notice we didn't use the control lines here. For simplicity's sake, we didn't show the clock pulses that would have coordinated the timing of this transfer. And so the control lines would have simultaneously been sending those system clock pulses. Okay, so if we tie all that together then, the address bus carries the location of the data the CPU wants. The data bus carries the data back to the CPU. And the control bus carries the coordination information. Now, in some cases, we have what's called a system bus that can be parallel or serial, which is beyond the scope of the discussion right now, but it'll combine the functions of the three buses. Now, what's the cost associated with this? When we share wires to transfer information, we lose some efficiency, but this does save us some cost in terms of both space on the motherboard and, of course, monetary cost in manufacturing. So we alluded briefly to expansion slots. There are various kinds of expansion slots on the motherboard. These are simply connectors where we can improve the functionality of our computer. This might mean upgrades of things like video cards, sound cards, network cards. These components have their own circuit boards, and when they're inserted into these expansion slots, they enhance the functionality of the computer. And one of these components is worth examining in a bit more detail. So a video card is the capacity to have improved graphics displayed on a monitor. It has its own processor unit, so it doesn't use the CPU for its calculations. It uses a graphics processor unit. It also has its own memory, its own RAM. And it may give us the ability to have different outputs for different kinds of monitors. So it can have VGA, DVI, HDMI, or even DisplayPort outputs depending on its configuration. And it'll also give us the capacity typically to have multiple monitors on our computer. It's specialized to look at two-dimensional and three-dimensional graphics in an efficient way. Sometimes it can even have outputs to TV, although this distinction between TV and monitor is really blurring a great deal in modern times. Okay, so our key points from today then. Internal computer hardware is fairly consistent across Macs, Android, and Windows PCs. Our power supply converts alternating current into DC current for use by the device. Our motherboard distributes power and information around the computer. Our CPU is the brain doing the decision making. Buses move information across the motherboard, and expansion slots allow us to upgrade and repair computers using one computer for different purposes. Video cards are an important component in modern times, giving us better two-dimensional and three-dimensional graphics and taking some of the weight from the CPU in terms of processing and memory. Okay, for your homework then, have a look at the internal hardware questions sheets and focus your attention on pages 2 and 3. Thanks very much, and have a great night.